Thank you. It's good to see you all and to see some of my colleagues in Tel Aviv. Happy birthday, Yuri. And it's your 81st birthday, I think 6 weeks ago or so. So enjoy. Yeah. So 10 years ago, there was a volume number 2 in this series of Fields of Logic and Computation, dedicated to Yuri Fields, because Yuri sort of means a farmer. So this was the idea. And there was a picture on the cover of a brass plate that spoke about planting and harvesting. And so the upcoming book, which will be the 4th in the series for his 85th birthday, will have a different plate from the same series by this well-known artist, and with the inscription that if I forget the old Jerusalem, may my right hand forget its cunning, which is appropriate. So just the other day, Weizmann Institute was hit by a missile, and this is how the labs look, unfortunately. So the motivation for what I want to talk about today is to have a language, a way in which to characterize asynchronous algorithms on the lowest level, so that it's completely generic and can describe any computation and any algorithm. And to do that, we'll use Yuri's abstract state machines, where the actions will be similar to the actions in the abstract state machines, but the control structure will be generalized so that actions can occur simultaneously or sequentially or independently, and all within the same framework. One of the motivating examples is, for me, was Dijkstra's guarded command, in which he has a conditional: if P is true, do big P; if little q is true, do big Q, and so on, in which the guards P, Q, and R can more than one can be true, in which case the intention is to choose between the different options. So if both P and Q are true, then either big P or big Q is executed, but if R is not true, then R isn't. But how exactly can we describe Dijkstra's intention here? Well, I looked at a bunch of descriptions and books and articles, and one of them here in a textbook on programming explains that upon execution, all the guards are evaluated, P, Q, and R, all 3 of them are evaluated. If none is true, then the whole conditional fails. But if some of them are true, 1 or more, then choose non-deterministically between them and then execute just one of the statements that are followed by the arrows. Well, this is not necessarily, it's certainly not the way it would be implemented, and maybe not even the way it was intended. So what I want to both be able to express is different ways of specifying how the conditions are evaluated and which command is executed and under what circumstances. And then something that's not considered by Dijkstra is what if one of these conditions fails or loops, because he was only looking at very primitive conditions like x greater than 0. But if P is some complicated program that can go into a loop, then what happens? What is the intention? And the point is to be able to express any and all choices about the semantics of this kind of statement. So, for example, if just you have two cases, P and Q, perhaps I want to test both of them. But if one of the tests succeeds before we even begin, before the other one, Q, starts, just because things are happening asynchronously, then we can abandon the alternative Q because we already know that P is true, and we'll do the capital P actions. And there's no need to also test Q. So I want to be able to say that the conditions are tested only if they have to be, but if not, then we can skip it. If we already know that, we can skip it. So overall, the difference between abstract state machines and what I have in mind is how finely we can describe control. We want to be able to describe it precisely, what the order and frequency of different actions and memory accesses are. We want to be able to say that a single step may have more than one atomic operation or action, and to be able to talk about choice. And for that, I'm going to describe a graphical language, both a graphical language for algorithms that specifies everything precisely, and also when we want to talk about the semantics, the operational semantics, what transpired, a similar graph can be used. And just getting ahead of myself, here's an example of Dijkstra's conditional, where you have this left branch for P and the right branch for Q, but taking into account the possibility of skipping one of the tests if the other one already succeeded. And we'll get back to this. Now, the inspiration for this kind of style of describing a process goes back more than 100 years. Flowcharts were sort of invented in 1921, and they're Petri nets and the Vienna definition language and various other things, culminating, in what I'm describing with abstract state machines of Urey's in '93. So this couple, Lillian and Frank Gilbreth, were engineers in the 1920s, and they were trying to help factories get more efficient, to have assembly lines work. And so they were interested in expressing what has to happen in what order and what things are contingent and other things. And they invented something called process charts that was later formalized and adopted by engineering institutes and so on. So that was back in the 20s. But in the beginning of programming, von Neumann and Goldstein in this report, they had flowcharts, as I learned in school when I first learned programming. And they have both actions here, like put one in I, but they also had like boxes for assertions. And Turing used this also later, the same time more or less, to describe algorithms. This is Turing's algorithm for n factorial in his report. And something that's interesting, they already discussed having boxes here for relations that are preserved in some invariant sense, but that's not the subject for today. Petri nets, okay, I see an expert in the audience here. But you have both data and control moving along these arrows in some sense. And the Vienna definition language had both edges for control and for data. This was maybe overkill, but a famous experiment in defining semantics. And the programmer's apprentice and Plotkin's structural semantics. In these cases, the vertices here represent actions, but the actions can be complex. Maybe plants or whatever. And when you want to plant some wheat, it's a complex action, not just one simple thing. You have to take it, put it, dig, and so on. So that what we want to do here is to have only atomic actions, but similar kind of structures. So the two main antecedents for the formalism I'm talking about are Urey's abstract state machines. And here's an example of one of what's called a workhorse algorithm for searching for a zero in an arbitrary function f. So what's in yellow here is the abstract state machine description of the binary search for the zero. If they're close enough, you look to see whether the sign matches one edge or the other, and then you narrow the region accordingly. But the point is here that F, you're not implementing F. You're getting F regardless of F, regardless of whether F is computable or not. This describes binary search. The second component is having control edges partially order the actions. And so Pratt has this partial order semantics and in multi-sets of actions and things and something like this, von Pratt. So, sorry, putting the two together is what I'm trying to do here. So what we're going to have atomic actions like an abstract state machines, only the basic read and write and the like. We'll have control and data moving around, passing control and passing data. The actions will be partially ordered, like in von Pratt, everything explicit, and the algorithms will be completely unstructured spaghetti. Turing's observation, I wrote in his famous paper, what are the possible processes which can be carried out in computing? He asked himself, what is the basic atomic actions? And he said, reading and writing, querying a location or cell on a tape. What does it say there? Or writing on it. So I'm going to use a circle and a square for these two actions in the graph representation. So the vertices can be a read, like this yellow X, or a write, like this blue X. And these are, I mean, what Turing rightfully understood to be the atomic actions that take place in an algorithm. Sorry. What Dury added to that, he writes, we sought more versatile machines than Turing's, which would be able to simulate arbitrary algorithms in a direct way. So for him, reads are generalized not just to look at a cell on a tape, but to apply any operation to arguments, like having an algebra of operations. And writing is to update the graph of this function f by changing what's in f of 1 to be something else. So it's a generalization of Turing to arbitrary structures, not just tapes. So for me, we'll have vertices that are these reads and writes. We'll see some other vertices soon. And they'll be connected by control edges, which I'm drawing in red, meaning that the write to X happens before the read of X. So you get the new value in the read. Also data edges, that you read the 4 and pass on that value along a channel, this blue channel, to the right, and so on. So those are data edges. And if you're not color challenged, then the purple here is meant to be both red and blue, that the edge from read 4 to write X is both a control edge, meaning that you have to read before you write, and also passes the value on. So the actions are only quasi-ordered. Some things can happen at the same time, some things can precede, and other things can be independent. You can say they're sequential when one has to come before the other in the control order that's shown by the red arrows. And the non-sequential if one doesn't precede the other, either because they're independent or because they happen at the same time. And I tried to draw a picture here. So here, the point is that reading y precedes taking the square root. Reading 0 precedes this comparison of equality down there. And reading x before you divide. So this is part of the graph describing the control order. In what order things have to happen when you want to, in an instruction like if the square root of y is not equal to 0, then put x divided by y into z. then that means you have to read x before you divide. You have to read y before you take the square root. You have to have the value of 0 in hand and the value of the square root in hand before you compare them. And you need the outcome of the comparison before the division. And the division has to take place before the assignment to z. Okay, and if you want things to happen simultaneously, then you can sort of put them in a circle like that. Now, besides the control, there's also values moving around. So in the graph we saw before, it didn't show where the divisor comes from. So if I want x divided by the square root of y here, and so values move around. If y is in the current state 4, square root of y is 2, you compare the value of 2 to 0, not equal, and then you take 6 divided by 2 in this case. So now, so if you have these graphs, you can, a parallel composition is just putting the two side by side, no problem. They're something on the left, something on the right, they're independent of each other, they're asynchronously executed. But that if you have things happening in parallel, you can have a problem of confusion. If you want to assign value of y to x in parallel with assigning the value of x to y, then these two can conflict. So this is no good. This kind of confusion, and one needs to impose some kind of order. For example, that you have to read x before you assign to x, because you want to assign the new value, a new value to x. But so the reading of the old value has to precede the writing of the new value, and the same thing goes for y, and that prevents confusion. Okay, to do things sequentially, like to do the thing on the left before the thing on the right, we can just draw a control arrow from the writing to f to the reading of y. And then we have no problem. These things won't conflict with each other because they happen sequentially. But we don't really need the whole first assignment to precede the whole second assignment. The only problem here is that the value of z that's being used by f shouldn't be changed before the assignment to f. So the only imposition of order we need here is that the read of z precedes the write to z. So the arrow only needs to go from z to z. Okay, so there are cases where you cannot, where you have some order of actions that you can't describe in a serial parallel thing, only using parallel, taking two things in parallel, two sequences in parallel, or two parallel things in sequence, or some combination thereof doesn't cover all possibilities like this diagram. Okay, so besides composing things, we need also means of branching. And so you have the obvious and an or, kind of where we'll see in a minute. For any programming language to be complete, you need some kind of conditional. So those are the first three. And then turned out, at least I think I need something which I'll call a probe, and I'll explain. So you can think of, describe here 4 kinds of choices. The first one, the conditional, is like, Dijkstra, or if E is true, do P, otherwise do Q. So we need the value of E, check it, is it true or false, and then go left or right accordingly. And then the control goes from out of P and Q, and merge in that open circle, because the control either from one or the other is enough to go on. So an angelic choice would be where we want it to work regardless, and so this is not the best. This is not really what one means by angelic, but we want it to work, so we have to try both P and Q, so that if P works good, if Q works good, I don't know which, but maybe the angel knows, and we'll do it. And demonic means let the universe decide whether to do P and Q and hope for the best. So it's just a choice, or either go to the left or go to the right. But the smart way is sort of what I was describing before, which is we want to try doing one and try doing the other. But if one of them succeeds, then we don't have to do the other. I mean, in other words, P or Q, whichever one works, if one of them works. But there's no need to do both. And that's what that red diamond means. The red diamond asks whether the green arrow is live or not. So in other words, the green arrow turns live only if control reaches it. And this tests the control. And if it's live, you go down. And if it's not live, you go to the right. And once a wire is live, it stays live. So if you see what's happening here, at first, we're going both left and right. On the left, we check that Q hasn't happened yet. And if it hasn't, then we do P. On the right, you check if P hasn't happened yet. And if it hasn't happened yet, you can do Q. And then whichever one finishes, we're happy. So on the left here, you have a conditional, sort of like I just described. And then you're testing R or S. And in one case, if R is true, then Y gets 0. If S is true, Y gets 1. If neither is true, then nothing happens. That's the diagram in the middle. So the diagram in the middle is a description of a specific computation. Computation in the case where R and S are false. So you take the right exit from the diamonds, but you can't do anything. So they lead you no place because you don't have the necessary control to go ahead and assign Y to 0 to Y or 1 to Y. If one of them is true, in this example on the right, R is true, so you take the left egg. R and S are both true, actually. So they both reach the choice point on the bottom and the circle, and in this case, the choice was to go right and assign 1. Back to Dijkstra. So what I said I wanted is that to test P and Q, but if one of them finishes successfully before the other one starts, then don't bother with the other one. And this is how one can describe that. So the left branch is P, the right branch is Q. And so you start out, you take both branches, that's the black circle, which is an and, do both. You test, has control, finish with going down the left. Has control reached the point after the testing the truth of Q or not? If yes, okay, if that green arrow coming in on the left is live, then you go down. And down says, well, either do nothing, go to the black circle and do nothing, or do P, go the other way and do P. But if Q's line is not live, then we haven't succeeded with Q yet, and then you have to, so you take the right branch out of the red diamond. I mean, I don't know, you can see it here. You take this branch out, and this is an OR, so you have to do P, and then you go down here, and then you don't have to do Q anymore. All right, so I'm not going to go into this elaborate example of a GCD, but normally you check is X, which X greater than Y or Y greater than X, and choose accordingly, and then subtract one from the other and so on. And so a computation may take one path with certain initial values, which are shown here on the blue arrows, or can take another path and that way. But a smart GCD would do this thing that we just described, and only testing whether X is greater than or equal to 0, or Y is greater than or equal to 0. We don't have to test both as soon as we know that one of them is true. Anyway, so this code is spaghetti, but it's a nice spaghetti with porcini, so it's the way to do it. So if we have this description language, then we have, in order for a graph of actions and arrows to correspond to a possible algorithm, we need to impose various conditions. For example, I'll call an axiom required, no forgetting. That's if you have a sequential reads from the same location, you read X or you read F of 15, that should produce the same value every time you look at that same location or the same variable or array or whatever, unless there's been a write to that location in between one read and the other. So reads should be consistent unless something happens. Same thing with a write. Once you wrote something, then every subsequent read should read the value that you wrote there unless there's been another write intervening. We saw this problem of confusion. So we need to impose that if you have two reads to the same location, that they're not sequential, or that they're in parallel, then they should both receive the same value. And same thing, non-sequential writes. If you want to write to the same location in two different places, that's only allowed if, and they're asynchronous, that's only allowed if it's the same value that you're trying to write both in both branches. And so if a read and a write are non-sequential, that only makes sense if what you're reading is the same as what you're writing. Okay, so we saw these black dots for junctions. I mean, on top split and do three reads, y, 0, and 1, and then so we saw these arrows for data flow. So the value of y goes to the square root operation, the value of the square root goes to the not equal, and so on. And these are channels that carry values, and they can carry them far away, not down the hall, and there are these controls. So regarding the channels, there's some other obvious things that need to hold. That the value that comes out of one end is the value that went in at the other end. And that if you have a channel, like, okay, you have this channel here from y to square root, that you're taking the square root of y. So you need to read y before you take the square root. So the value of 4 is going from y to the square root. The control has to be in that direction. The read has to be before the square root. Otherwise, the value is, so in other words, a blue arrow can only go from something that is in the transitive closure of the red arrows. And then if you have more than one channel coming out of the same vertex, they should all have the same value. Skip. So you can have a short, what's happening here is that the value of the square root of y is going to two places. So out of the square root, you have two blue arrows. You're using that value both for the comparison, is the divisor going to be 0, and you use it for the divisor. So you read once and you use it twice. Okay, so, and more generally, you might have an operation that said there, you can have two outputs. So you do division here, you might have both the quotient and the remainder. Or you do square root, you might have both square roots. All right, so let me, this is what you would do in a programming language with the let statement. Let t be the square root of y, or more complicated operation, and then use that temporary value t in more than one place, like z is t plus t. So the t here is a way of describing the channel that's carrying the value of square root of the square root to two places, to the two inputs of the plus. So this covers the use of like a let statement. We saw you have no trouble here with arbitrary connections as long as they meet those requirements of the axioms. But you can have minimal constraints that you may need the read of z before you apply g. You may need the write to y before you want to read that new value of y. And the arrows only need to make the necessary constraints and not put a whole statement in front before the other, because you can just put an order on the atomic actions. Okay, we spoke of compositions. Sorry. So you can also have a sequential. So if you have a sequential composition like this, and I said you don't need the one on the left to completely precede the one on the right. You only need the z to be read before it's written. Okay, so here too, you want to swap x and y twice. You again only need to make sure that that the new value of x precedes the new reading of x, but you don't need, so you only need these arrows. You don't need both x and y to precede both x and y. You only need x to precede x and y to precede y. All right, so we have conditionals. Here's some more complicated let. I'm skipping. And so, as I showed in an example before, demonic, the don't know choice, let's see, I mean, I don't know which is going to happen, and I choose, and if I may make the wrong choice. That's in the demonics, the idea that I always make the wrong choice. Here, I just might make the wrong choice, and the open circle was choose one or the other, and it may be the wrong choice. Angelic, which means don't care. Well, if you don't care, but you don't know which one to choose, they better do both. So here's an example of demonic. If something is false, then assign 0 to z. If false is true, then assign 0 to. Never assign. That's never going to work. And if t is true, which it always is, then you have the value of 1, which you want to assign to z. Demonic may push you, may help make you choose the wrong one, and then you go to the impossible branch of if f and 0, and then you're stuck. So the demonic like that would fail because you chose the wrong branch and you can't proceed. If you happen to choose the right branch, then you go the other way and you do succeed, but you might not succeed. Okay, so you might get this. Angelic means do both. And then if one is, the only one of them is true in this case, and that's what happens. So to summarize, we have data flow in the blue arrows, and the main idea is that you can't retrieve you can't use a value before you've retrieved it. So the tail end of the arrow has to come before the head of the arrow in the control order. Values need to be consistent unless something changed them. So I tried to put all the constraints that I know in a list here, that if reads produce the same value unless you wrote something in between, or you write something, you're always going to read that unless something happened in between. The value of a location doesn't change. You know, if you don't do anything, it's stable. It's not going to change unless you do something to it, change it. And non-sequential reads will give you the same value on some things I've said before. And that the channel is faithful, and that so that in a program, if you ever use a value, it has to have been produced someplace. And as I said, the two ends of each channel are ordered by control. This I can't explain. And thank you very much.